Right. And so in the previous session we have seen about temporal coherence, the coherence in time domain, and we have seen about study of waves. So waves can be studied as a function of time and as a function of displacement. I mean as a function of space. So basically wave is a displacement from mean position. So if you take a string, it will be straight. When you generate a wave, there will be displacement from mean position. To and fro. There will be to and fro displacement from mean position. So study of waves implies study of displacement. So that displacement can be studied as a function of space at various locations in space at a constant time, or at a fixed location in space at various times. Both will give you similar results. You will get sine wave as a function of time and as a function of space. But both should be connected. So the variation of displacement as a function of time and the variation of displacement as a function of space should be equal. I mean, should be connected. If you see the dimension formula, that connecting parameter has the dimensions of square of velocity. So on one side you have variations of time, and other side you have variations of space. Both are equal means both should be independently equal to some constant, and that constant is velocity. Because here on one side only time is varying and on the other side only space is varying. So if both are equal means this variation should meet a constant. So that constant is velocity, and to obtain the velocity we have to multiply the constant parameters we have defined in each domain of study. In space domain we have defined wavelength, and in time domain we have defined frequency. So product of those two constant parameters will give you the constant connecting parameter. So velocity remains constant. Implication is if you raise the frequency, wavelength reduces. So the same can be observed even in a string. If you raise the frequency, number of oscillations, the wavelength reduces. And when light enters a different medium, frequency changes. I mean frequency remains constant across the boundary. Otherwise the wave gets disconnected. So if on the velocity reduces first of all. When light enters a denser medium, it interacts with more and more molecules or atoms. So light gets slows down. So when it slows down, we have 2-3 possibilities. Either we can reduce only frequency, or we can reduce only wavelength, or we can reduce both. So if I reduce the frequency, what happens? So on the one end you have high frequency, on the other end you have low frequency. So there will be a disconnection of waves. So to avoid that, we have to keep the frequency constant, and entire reduction is imparted to the wavelength. So when light crosses a boundary, when light enters a different medium, wavelength changes but frequency remains constant. So higher the wavelength, higher is the angle of refraction. So different colors will have different refractions. So red color have larger angle of refraction, blue color has a lower angle of refraction. So because angle of refraction is proportional to corresponding wavelength in this case. So different colors have different wavelengths, and so different refractive indices. So now the refractive index of water is 1.33 is what? It is defined for which color? I mean, we have seen all colors have different refractive indices, different angle of refractions. So This is defined for actually yellow color 589 transitions, because that was the only monochromatic light source available at that time. So otherwise we would have taken average of blue and red, 3000, 7000, average is 5000. So we would have defined it for green color, but it is defined for sodium yellow 589 transitions. Refractive index is defined for sodium yellow, because that is the only monochromatic source available. So now coming back to this coherence. So light emits in the form of photons, means packets of waves, wave packets. So when two or more wave packets emitted at the same time overlap, we'll get a high amplitude wave packet or high intensity photon. So okay, here the two photons emitted at the same time. On time scale, both are emitted at the same time. So we get constructed interference and amplitude increases or intensity increases. What if the photons emit at different times? So here, as a function of time, if a set bunch of wave packets emit at different times, we'll get a wave. But the wave is disconnected at the junctions. Right? It may not be overlapping smoothly. We may find some disconnections, or we may find some discontinuities at the edge of each wave packet. Okay. So at the boundary of each wave packet, we will see some disconnections. So that is the issue. So when we look for constructed interference forever, let's say both waves started at the same time, but at the boundary, one wave and another wave may have smooth overlap. So if the second wave has smooth overlap, then we may see destructive interference also. At some points, at some portion of time, we may have constructive interference, and after that we may have destructive interference. Both are possible. So to keep the interference constructive forever, these wave packets should overlap smoothly over a period of time, and I am defining that as coherence time, the time over which the wave packet maintains its phase constant. So there is a small correction here. So this is defined for a single wave packet, single wave train. So the time over which a single wave train maintains its phase. So we have to fix 2 observation points on a single wave train, and we have to measure the phase difference between those two. So here both are in the same phase. So the phase difference is 0. So as the wave progresses, if there is any disconnection, after some time you may have, if you shift it by 2 units or 3 units, at some time you may get, so let's say this is 1 and 2 first observation points, 3 and 4 are second observation points. So the wave is progressing. So at the beginning we are seeing 0 phase difference, and after some time 180 degrees phase difference is observed. So this should not happen if we wish to have constructive interference forever. So I am defining this coherence time, the time over which 2 points on a single wave train maintain constant phase difference. So time over which 2 points on a single wave train maintain constant phase difference. So that is the coherence time. So this is the coherence time, at the time over which 2 points on a single wavetrain maintain constant phase difference. Okay, so if we reflect this, so here on x-axis we have time. So if we reflect the study onto space domain, we can define coherence length. So it is the product of coherence time multiplied by velocity. So in this graph, we take position on x-axis. So at various locations in space, let's say we take 2 points in space. Here it is 2 points in time domain. So my starting point, I consider it as 1 second, and I measure the phase at 10 seconds. This is the first observation, and second observer might be observing at let's say 8 seconds, and then 17 seconds, at a gap of 9 seconds, let's say. So first observer collects the data at 1 second and 10 seconds, second observer at 8 seconds and 17 seconds. So if they both report the same difference, the wave is coherent. So the same study can be extended to space domain also. So here the observations are made at whatever, at 1 unit and 10 units distance. Second observer records their observations at 8 units and 17 units distance. So that we can define coherence length. These two are connected by velocity of light. Okay. So this coherence is called a temporal coherence because it is basically defined for time. Okay. So if we wish to have infinite coherence time, means the wave remains in constant phase or maintains its phase forever. There are no discontinuities, there are no disconnections between wave packets. All wave packets overlap smoothly over time. Then the wave will remain smooth forever. So if I wish to have infinite coherence time, the corresponding variations in frequency must be 0. If I wish to have delta t to be infinity, delta nu should be 0. So coherence time becomes infinity only when frequency differences are 0. Means for all monochromatic light sources, temporal coherence is infinity. The wave remains intact forever. So for all monochromatic light sources, we can generate constructive interference easily. So the well-known monochromatic light source is sodium, yellow, but it has two wavelengths with nearly separation of 6 angstroms. So it is 5890 and 5896 actually, and we take 5893 as the average of those two. But actually it is a doublet. It has two wavelengths with a separation of 6 angstroms, 5890 and 5896. So if we calculate the change in frequency, so how do you do that? Delta nu is C by lambda 1 minus C by lambda 2. So if we calculate this, delta nu will be around 52 hertz. frequency variation for sodium electrolyte. So it is not constant, it is spread over a span of 52 Hz, around 5893. Sorry, 5893 is the average wavelength. So average frequency is 509 terahertz. So around 509 terahertz, it has a spread of 52 Hz. So delta nu is not 0 for sodium malolite. It is 52 Hz. So there may be some slightly disconnections. So coherence length is not infinity for sodium malolite. It is a finite value. Coherence length is not infinity for sodium malolite. Same time coherence time is not infinity. It has some finite value. Right. So temporal coherence is defined for a single wavetrain. So we'll be considering 2 points. We'll be measuring the phase difference between 2 points at various times. So this is time axis. And so if I call this as tau, for tau to be infinity, delta nu should be 0. So all monochromatic sources will have infinite temporal coherence. So next one is spatial coherence. Spatial coherence deals with phase difference between 2 points on 2 wavetrains. So here we consider 2 points on a single wavetrain. For spatial coherence, we consider 2 points on 2 different wavetrains. The phase difference between two points on 2 wavetrains. Should remain constant. So for this to happen, the waves should travel in same direction. So the difference remains same. Wave should be unidirectional. So laser is the best example for spatially coherent light source. Parallel one. Example laser. Unidirectional or parallel? So here we can define coherence area. Area over which two wave lengths maintain constant phase. Here it is the coherence time. So here we can define coherence time and coherence length. Here we can define coherence area over which two wavetrains maintain two or more wavetrains. So if you have multiple waves, you can cover more area. So it is the area over which the wavetrains maintain constant phase. It's coherence area. So if there is if I take a point light source, the waves will be traveling in different directions starting from the source. So then, if you take the phase difference, it may vary. Right? Here all waves have same phase difference. Here it has changed. Here things may change. So, for two waves to have spatial coherence, they should be parallel. Okay, so point light sources cannot generate spatially coherent light. If you take sunlight, rays are parallel. Why so? Why sun rays are parallel? So if we see sun as a sphere, if we are able to see it as a sphere, the rays or waves will be diverging in different directions. Then we cannot get spatial coherence. But the light rays received for us on Earth are actually, this distance is millions of kilometers. So the light rays reaching us are actually starting from two nearly separated sources, very nearly separated sources. Then only we are able to see them. So the arc angle is less than a few seconds, thousands of seconds. Okay, if the starting point has an arc angle of even 1 second, it would have traveled crossing the Earth. So the light rays that we are seeing with our eyes with a separation of 2-3 inches might have started from almost two near points on a same source. Right? So by the time they have traveled millions of kilometers, even if you have 1 second arc angle, it would have been miles and miles of kilometers. Thousands of kilometers apart. So the rays we are seeing here are starting from almost near point on the sun. So to have spatial coherence, the light rays should start from a single source, I should say. Single source or two closely separated sources. So examples: temporally coherent and spatial coherent. Candlelight, candlelight is not temporally coherent, it is not spatially coherent, it is not monochromatic, and it is a point source. So it is not temporally coherent and it is not spatially coherent. Sunlight, is not temporally coherent, it is not monochromatic, but it is spatially coherent. Sodium light, is temporally coherent but not spatially coherent. And then laser, both temporally coherent and spatially coherent. So if we use lenses and keep the sodium light at the focus of a converging lens, yeah, it can be spatially coherent and temporally coherent, sodium light. So, to generate construct interference forever, or to keep the interference pattern forever, we should have the interfering waves to have both spatial coherence and temporal coherence. So, it is more easier to generate interference pattern using lasers or sodium light using lenses. Okay. So now, generation of coherent sources can be done in two ways: by division of amplitude and by division of wavefront. So we have to generate two similar light sources from a single source. Then only we can observe interference pattern. So if you take two different light sources, you cannot generate interference pattern, because though they may look similar, they may not be exactly matched. So we have to generate the two sources from a single source. So we have to split the given light wave into two parts. So there are two ways to split the light wave into two. One is by division of wavefront, another by division of amplitude. So what is wavefront? Wavefront is a locus of points with constant phase. Locus of points with constant phase difference. So if we connect all the peaks or if we connect all the crusts, we get a wavefront. So we have to connect the locus of points with same phase difference. So that is called wavefront. And each point on the wavefront acts as a source of secondary wavefronts. Each point on the wavefront acts as a source of secondary wavefronts. So if we use slits, this wavefront will get split up. So this is a matter of discussion that we will see again, that each point on the wavefront acts as a source of secondary wavefront. That is the starting point for diffraction. Means in diffraction we will have superposition of waves starting from 2 points on a single wavefront. In interference we have superposition of waves from 2 different sources, 2 coherent sources. Whereas in diffraction, we have superposition of waves from 2 points on a single wavefront. So the details of that we will see during diffraction topic. Because if you see here, the light rays are traveling, let's say, in this direction, here in this direction, here in this direction. So they are traveling in different directions like this. And once you fix a point, this point now acts as a second source of secondary wavefront. Means from here light rays can travel in all the directions. So how is that happening? I mean, initial source is in this direction, but how come we are able to generate a ray along other directions is a matter to discuss. Okay, so that we will see during diffraction topic. So as of now, each point on a wavefront acts as a source of secondary wavefronts, and that is how, I mean, we can use slits to split the wavefront into 2. Another possibility is by using 2 prisms. We call it as biprism. Biprism, where light rays from a single source fall on 2 prisms connected base to base. So biprism is 2 prisms connected base to base. So here the light rays seen at this end seems to be coming from this source or virtual source, and the light rays seen at this point seems to be coming from this virtual source. So two virtual sources are generated from a single source. So these two act as a coherent light source. So on the other end we can see interference pattern. So another possibility is using Lloyd mirror. So here the light rays reflect on a mirror. One set of light rays reach the observer directly and another set reflect on a mirror and reach the observer. So as if the reflection portion acts as a second source. So this is S1, this is S2. This is a mirror. So here S1, S2, this is the actual source. This is S, S1, S2. So we are able to generate two coherent sources from a single source by division of wavefront. So next one is by division of amplitude. Then how to divide amplitude? What is amplitude? So when you have constructed interference, amplitude increases. Then how to divide amplitude? Means we have to reduce the intensity. We have to split the intensity into two parts.
Half amplitude and half amplitude.
Yeah. So we have to generate two waves from a single wave by reducing the intensity. So we have to split the given light source into two lower intensity sources. So we have to use either mirrors or reflecting surfaces or refracting surfaces. So let's say when light falls on a material, a part will be reflected and a part will be refracted with a division of amplitude. Let's say if we start with amplitude A, this A is what? So amplitude gets divided. So we have to use reflecting or refracting surfaces to develop two coherent sources. By division of amplitude. So if we use a thin film, a portion is reflected, a portion is refracted, and it reflects again on the lower surface. Now here you can see interference pattern. So these two sources now act as a coherent sources. Similar are the cases with Michelson interferometer or Newton rings. So in Newton rings, light rays will be reflected on air film trapped between two glass surfaces. So one light ray here, another on the bottom. So this is S1, this is S2. The reflections take place on the air film between the two glass plates. One is plano-convex, another is plane. And next arrangement is Michelson interferometer. So this is Newton rings. So what about Michelson interferometer? We take a glass plate, semi-silvered glass plate. So the light rays, a portion will be reflected and a portion will be transmitted to the other end. Here a completely silvered glass plate will be there. So this is partially silvered, so a portion will be reflected and a portion will be transmitted. So on the top portion we have this is called beam splitter. The semi-silvered glass plate is called beam splitter. So it splits the light rays into two parts. One traveling upwards, one traveling along the incident direction. So beam splitter generates two perpendicular light rays if it is set at 45 degrees to incident light rays. So on the other end we set two perfect mirrors. Then we can see interference pattern here. So this acts as a source 1, this acts as source 2. So beam splitter generates two mutually perpendicular light rays if it is set at 45 degrees to incident light rays. So then the two rays are reflected back onto the beam splitter by using two perfect mirrors. Then those two light rays will generate interference pattern. So one mirror is here. So now the pin setup. So here another mirror. So from the beam splitter we get two mutually perpendicular light rays. After reflection from the mirrors, we get two coherent light sources that generate interference. So these are the two methods of generating interference, one by division of wavefront and another by division of amplitude. Yeah.